because I figure it'll be useful. And to that end, I have this screen share going. Oh, hello, everybody in the recording that I just started. We're looking at A-Mir-Formality. Okay. And I'm going to send out, though, the link if you use, oops, however I do this, if you use VS Code, you can join, and it's nicer maybe than seeing it in the screen share. If you don't use VS Code, you should. I don't know. I like it. I say that as an Emacs person. I was having a hard just yesterday arguing with somebody at AWS, and they were trying to sell me on Emacs, and I was like, dude, I've been there. So what are we going to do? That's the question. What Will and I did yesterday, and I thought it was pretty fun, was we implemented the rules for the drop trait. In particular, this rule that says that the drop trait always has to cover all potential instances of a struct. So we kind of added in that logic and how you would express that in A-Mir-Formality. I thought we might do something similar, like for the copy trait, maybe. Just because it seemed like about the right level of complexity that we could actually do it or get close to it. Does that sound good?
Yeah, for folks that don't have, you know, who are coming to this completely cold, there is some documentation in the repo. It's not fully rendered online yet, but that'll give you kind of just a very basic understanding of like what this thing is, how there's kind of different layers to the Redx code that sort of take different levels of abstraction.
Yep, and the layers are pretty, we'll see them at play, but they're pretty important. All right, so let's do the copy trait. What we did yesterday, and I'm going to do the same thing today, is we did a type-driven development kind of thing where we first wrote some tests and saw them fail before we went on and tried to fix them. In my experience, that's a pretty good fit for Redx because there's like a million ways for you to not be doing what you think you're doing, mostly involving not having enough parentheses. And so, I don't know, I like to do it in small enough pieces where everything runs. So let's start with this. First of all, we're going to be working at this declaration layer, which is right now the highest layer that's really populated. It kind of is the first one that actually, no, well, there's the declaration layer that understands Rust declarations, the type layer that is kind of just the Rust type system in isolation without much knowledge of anything else, and then the lowest level layer that's independent from Rust entirely and just handles how to logical predicates and how to solve them. So we're going to make a test for the special rules of the copy trait. And the main rule of copy is that you can't be copy unless all your fields are copy. And so let's see. We would like to say, well, first of all, impl copy for 32. That should be okay. I think there is a rule like that in the standard library. I adopted this convention, which I'm sure won't last forever, but it's fine for now, where for the lang item traits, I'm giving them this special name that begins with Rust : So one thing about scheme is identifier is basically anything that doesn't have a space in it. So you can throw colons and other weird stuff in there, which is nice. So let's look at this declaration. The first thing we're going to do in this test is we're going to build up the program that we're checking. So redx let, that's basically a let statement like in Rust. It just assigns a series of variables. In the case of redx, every variable has a name that has, every variable basically carries its type because it begins with, the name of the variable has to first be something from some non-terminal from the grammar, right? So this is the declaration grammar, which extends the type grammar. And you have things like, oh, a crate declaration is a series of crate declarations, or sorry, a crate decals is a list of crate decal instances. A crate decal is the name of a crate. And then the contents is the keyword crate, and then a series of items. I said the keyword crate. There's nothing about this that lets you know it's a keyword in isolation. It's just that it's not defined anywhere else. That's what makes it a keyword. So there's a lot of things like that, which is exactly where I said there's a lot of ways to write code that isn't quite doing what you think it is if you don't run it and test it. That's an example where like you might think you have a keyword or not have a keyword, but nothing sort of explicitly says it one way or the other. I've adopted the convention that non-terminals begin with capital letters and look like Rust type names, which kind of at least makes that relatively clear. So a crate item can be one of these four things: an ADT, like a struct enum or union, a trait implementation, or a constant, and so on. Right. So the idea is these non-terminal names.
You go notably we haven't started modeling functions yet.
Oh yeah, I didn't do that yet. Be good. That's a good addition for another day. So who needs functions? You know,
exactly.
In my world, executing is secondary. So right. So this is a trait decal, right? That's this non-terminal here, and then the underscore you can optionally, like, this is a perfectly valid variable name, and it's actually pretty common. It just says the trait declaration and sort of works best if there's only one, right? A lot of times you only have one thing of any given type. So, but if you have more than one thing of a given type, you want to distinguish them from one another. So then you put an underscore in some distinguishing name. So here we have the trait decal copy. This term, actually, I don't think we talked about this yesterday, Will, but what's happening is that you're kind of in two worlds. There's scheme world, or racket, I guess, racket world, and then there's regex world where things are in this program grammar, and term goes from racket into regex. So this could really be an arbitrary racket expression. So, you know, things like +1, 2, or whatever, to add those two numbers, this would make, well, this would result in 3, which would then generate an error because 3 is not a valid trait declaration. But when we say term, then this stuff gets interpreted as a regex expression, as a regex term rather. Move my camera out of the way, which means, basically means anything that you, any like random words like trait will be treated like keywords, and lists are just like this is a 3-item list and not a call to the function A, if you know racket. Maybe you don't, doesn't matter. So we've got the way we model traits. They have first the name. I always put the name to the left just for convenience, and then the details. And in this case, this is a trait. This is the list of generic parameters. There's 1. So this is a list of length 1. The one thing is the pair of the kind of the parameter. It's a type. And its name, self. Right. So we make the self parameter on traits explicit. In Rust syntax, it is implicit. And then what would go here is a list of where clauses, but we don't have any, so there isn't one. I guess, no, I don't. Copy doesn't inherit from sized, does it? I don't think so. Clone does, annoyingly. And then in here would be the list of items in the trait, right? If there were functions and things, but we're not really modeling those yet. So that's an empty list. Okay, that makes sense. I hope so. Feel free to interrupt me. The next thing we're going to add to this test is an implementation. Implementations are a little funky because unlike other trait things that go in traits, they don't have names. So they're just an impl. This list is the list of type parameters on the impl. There are none. This is the trait and its parameters for which we implement. So this is the name of the trait. This is a list of parameters to the trait. There's exactly one, which is the scalar type I32. So this scalar tie, what that is, if you go to definition here, that is a function. So that's the other thing in regex. You can make lists and stuff, but if the first thing in the list is a function that's in scope, then it will be invoked. It's kind of like a macro. You could think of it like that. So in this case, this is a shorthand that I added because scalars are just in our classification, they're just a kind of rigid type, meaning that they're only equal to themselves, essentially. This is actually, well, this is how I'm currently modeling it. I think one thing that Will and I were discussing is that it might be nice to tweak some of these things to make these tests easier to write. Like, I wish I could just write I32 here. We could do that. We're not going to do it today. So this would be an implementation of copy for the type I32. This would be the list of where clauses. There aren't any. The way that you know what these things would be, by the way, let's see. I think I can't just go to definition for this. No, I have to go, is that you look at the grammar, right? So trait item decal, here it is. So this is where the list is, right? There's a list of kinded var IDs. A kinded var ID is a pair of a kind and a var ID. So this is a list of those. That's the generics. That's the trait that got implemented, the where clauses and so on. Okay.
So those are all required?
I mean, that's the structure of, that's the grammar, but these can be empty lists, right?
So it's not like, and it's because of that impl keyword that's not just like a list of other non-terminals that this could be.
Yes. Not sure I understand the question actually.
So like some others are.
So, okay, the impl keyword, I think I know what you're asking. If you didn't have this keyword, it would be totally valid to have like some other kind of decal, to have two non-terminals that both match to the same set of things. And when you do the pattern matching, you couldn't really tell the difference between whether something was originally a trait impl decal and you just called it a some other kind of decal or not. That's sort of like a subtyping. We actually take advantage of that on occasion where there's two different grammars, but they share a common subset, and you can sort of, if you're in that subset, you can cast back and forth between them. That makes sense. Was that the question?
Kind of. So like, for instance, oh, it's the parentheses. So like up at line 19, create item decal.
Oh, yeah. It's
that's
the
like a create item decal can be either an ADT, a trait impl, or a const. Like, yeah, here we're not saying a trait impl decal is either a kinded ID, a trait ref, or where. We're saying it is.
Right. It has nothing to do with this word impl. It has everything to do with these parentheses.
As it often will.
So you could have more things in this list, you know.
Cool.
But we don't.
And then since I suspect that this kind of pattern that we're doing right now is something that people will want to experiment with, can we go back to that redx let statement? And just, can you kind of just show us what the like scope of the like parentheses are? Like, because let means we're kind of like binding some variables.
Yeah. So like, right. So let, the way the structure of a let in scheme and in redx and in racket is, first you have a list delineated by a parentheses. Actually, racket lets you use, you don't have to use parentheses. Could use like brackets, but anyway, you'll see I do that in some places. It has, basically it looks like this. Let me make it more abstractly. A redx let is a list of like variable name and then variable value, pairs, and then a body. And this body will be evaluated with each of these variables in scope. And this star, there's both with and without the star. The star means that each variable is available in scope immediately. So like if you have variable name 2, this could reference variable name if it wanted to. Whereas if you don't have the star, then each of the values is independent and the names all come into scope only in the body.
So our pairs are trait decal underscore copy and then
name.
So we're
this is a variable name and this is a variable value right here.
Okay, great. That's super good.
And just for fun, actually, let's mess this up. Let's suppose that we had an extra pair of parentheses and see what happens. Don't know if we'll get all the way. We'll see how far we get. Okay, well, let me show you the first thing. There's two ways to run tests. Racco is like Racco is kind of Racket's little wacky command line thing. We don't really have a good equivalent to this in Rust, I guess. We should probably. That accesses various bits of functionality. I guess you could kind of like cargo. One of them is that it can run tests, and you can just kind of give it a path. I like to do J14 and -T. J14 means run using 14 threads. That's how many cores I have. The path, so if I run source, I'm going to run all the tests that are found in the source directory. And it's going to take a little while because it's not the fastest thing ever. But that's okay. And we will see that this test fails, I hope. But what we'll also see is that the error message you get when using Racco, or the backtrace you get, is not that great. It may not be too bad in this particular instance. Yeah, so you can see we got a failure here. It said that this term that we wrote did not match the pattern we expected. And this is a good example of why the backtraces can sometimes be not that great if you're using Racco. You know, none of this is my code, right? This is like error.racket. This is sort of talking about my code, but it's not the file name of my code. And this is some other thing. So what's happening is that there's like layers and layers of macros. And if you just run in Racco to make things go faster, they don't save all the expansion backtraces. So you're only seeing the actual macro definitions, which are not that interesting because I don't, you know, you're not familiar with them. Oh, by the way, the -T shows a table, and it just kind of shows you like where was the actual errors. Oh, there was one error in this file. That's why I like it. So what you can do, there's this wacky command that we have to record and probably make a shell script or something, so we don't have to keep typing it all the time. If you run Racket manually and you tell it to link in the error trace library, then it does much better backtraces. This is saying also include Racket, the base Racket libraries, and then this is the thing to evaluate. And what I'm evaluating is I'm importing the module, which is the submodule test found in this file. So I didn't emphasize it, but we're declaring things in a test submodule. You don't have to do that, but it's nice when there's also code in the file to separate it out. So if we rerun this, only I put the right file name in here. With the Racket command, with the error trace, we're going to get a much better stack trace that actually tells us where the problem is. So that's useful. Let's see. Yeah. I guess in this case, it's not that much better. Usually it is. I guess because it's done. Well, this case is not much better, but usually it's pretty good and tells you exactly the problem. In any case, we don't want the extra parentheses. So now we have the trait, we have the impl, we have what this says is I'm going to make a crate, and this is a list of the things in the crate. It has the trait and it has the impl. I could have, like, there's no reason I have to make these intermediate variables. You could just inline everything directly in here if you wanted. The reason I don't do that usually is because this way I'm like, if you make a mistake somewhere in there, we're just going to find out, oh, this is not a valid crate, and that's all. And that's not that helpful. This way I can localize my mistake to the exact location. Okay, and then what this does, this line is interesting. Create the environment for checking things in this crate. So the environment is like, contains all the, it's what we use to do type checking and trait matching and everything else. And when you make an environment for a crate, it's going to include, it's going to go through each of the items in the trait, in the crate, and generate the rules for them. Well, it's done that lazily actually, but right, it's going to make an environment. So this is a shorthand for saying that there's a single crate, and we're going to make an environment from that. There's a longer form that takes a full list of dependencies if you wanted to have more than one crate. which would be important, say, for the coherence rules to be able to separate out like which crate is the impl in. And so forth. So the way this actually works, I won't go too much into that, but it uses, this just creates an environment that carries a little hook that has some lambda functions that we can call later to do things like say, give me all the clauses that might prove this predicate and so on. But now we have this environment, and now we can actually write our test. And here we want test can prove. That's a test that says we should be able to prove, given this environment, that this crate is well formed. So the OK goal, or is OK. The OK goal basically says all the type checks and checks were successful. You could generate code from this crate if you wanted to. So right now that means the well-formedness checks, but if or when we add a type checker and stuff, that would mean that the functions also type check and so on. So now we should be able to run this test. I think this test will pass because we don't know anything about the Rust copy trait yet, and we have no reason to say that this impl is not legal. So it should work.
I think you want trait decl copy on line 24.
Oh, good point. So yeah, the test should not pass, and indeed it did not. So this is worth pointing out. This is a common error. If you have a mistyped variable name, it just gets interpreted as a keyword. So you see that in my error message, I have this random trait decl drop. That's usually like, if you see that something doesn't match the pattern, at least for me, it's always one of two things. Either I had a typo somewhere, in which case I see some random name like that looks out of place, or I don't have enough parentheses. And that usually happens when it's like a list of lists, like this is a list of length 1, but it sort of looks like a list. I don't know. Anyway, now it should pass. And we can start to write the next test. So I want to write.
Trace doing? And
what's that? What's trace doing?
doing?
That's a good question. Traced is a so passed, yay. No, wait, no output equals good. Traced is a macro which I wrote that brings that uses this redx function to say, here's a list of meta functions, meaning functions in the, not functions in your program, but functions in your type checker, that we want to trace as they execute. So it's for debugging. So for example, we could go into, let me just show you this. This crate OK goal is itself a function. Right? We could say, I'd like to see every time you call this function, what are its inputs and outputs, because something is not working right. So we could add crate OK goal into that list and run the code. And we will see what goal are we trying to prove in the first place. Despite the name, this can also trace judgments and things like that, which I haven't talked about today. But so yeah, so here we see
current traced meta functions is a redx function that
it's
provides that, and you just
functionality,
gave it a nice name.
Yeah, I just made a nice macro around it because a lot of times I like to have, especially if there are many tests, I want them.
Yeah, for sure.
So right, so here you see this is the function call. This tells you it's coming in, and then coming out, this is the goal we actually had to prove in order to show that this crate was well formed. And this goal is computed by essentially looking at each item in turn and figuring out what would be its correctness criteria. So in the case of the copy trait itself, this is the rule. It has some stuff up front, but you can see that it bottoms out in proving that all the things in this empty list are true, which is true. So this is just true. And if we were to optimize, we could get rid of it. And this rule is a little more interesting. It comes from the impl, and what it's saying is, what is it saying? Oh, right. It's saying that it seems like a tautology, but it's not quite. It's saying if you assume that all the types in my impl line, like I32, are well formed, then the trait copy is implemented. And like I said, it seems like a tautology because you have the impl right here, but the reason what's really happening is that the implemented predicate is only provable if all the super traits are also implemented. If there is an impl for this trait and all the super traits or other where clauses on the trait declaration. So this is really checking, did I implement all the super traits? Okay. So now I want to make a test that fails. Or that should fail rather. Or yeah, an error that, a test that should have an error, but won't. So we could make a struct foo of t, or just foo, I guess, would do. And then a struct bar. It has a field of type foo and implement copy for bar. And that should be an error because we want is not permitted because foo copy does not hold. Of course, it will be allowed today. So to do that, we have to go over into drop. We have to copy and paste some stuff. There we go. We want to add in, well, let's put it down here. Oh, that's good. We want to have this struct foo, and there's, so for a struct declaration, that's an ADT declaration. It's a struct. We don't need any generics, so we can take this out. So it has no generic parameters. No generic parameters. It has no where clauses. And what this is a list of variants. So in an enum, there would be multiple variants potentially. But in a struct, there's always exactly one. I have been calling it after the struct itself. Every variant has a name. So this would be like some and none for option, right? But we don't know, we can establish a different convention. And inside the variant, there's a list of fields, but we don't have any fields. So this should be all set. And then we need a bar. Bar does have a field. So we'll go in this list. We'll add, it's called, what did I call it? F. And the type of F is foo. So that's a tie rigid foo. What's this? Tie rigid, that's the kind of type. That's the name of the ADT. And this is the list of type parameters. There are none. So this is the one field we have in this list. My usual formatting convention is if this is a list that it would make sense to add more things into, like it's an open-ended list, then I put the closing parenthesis on the final line, just so then you can just press enter and put more stuff. Whereas if it's a tuple of a fixed, arity, then I don't bother with that. Okay, so now we have two structs, and we want to change this to be bar. So instead of scalar type I32, we'll put tie rigid bar empty list. And then we have to copy in these declarations. I think we're ready to run our test. Oh, almost. One problem. Which is that this test is meant to say that we cannot prove that this crate is okay because it shouldn't be valid. But the test will fail. Did that all make sense?
Does the order of declarations matter in the crate decal?
No. Okay. I just tried to match the order that I wrote them in. Okay. Well, I guess I would say, it doesn't matter. You could imagine it would matter if we were going to model macro expansion or something, which maybe someday we will, but I have no intention of doing right now. Because macros are, I think, the one place that order of item declaration does matter in Rust today. So, right, our test failed. This decal test cannot prove just It's not some built-in thing. It's actually a macro that I added, which, so defined syntax rule is like macro rules, right? It says cannot prove for an environment a goal, and all it does is it tests equal to false this regex thing that says, can I prove this judgment? So that's why you see actual true, because it was actually successful, and expected false. Okay, cool. So we got our test, it doesn't work. How do we fix it? Well, what we want to do is go into the rule, go into this function, create OK goal, and change the OK goal for the trait to reflect the extra conditions that the copy trait has, right? And so we've set it up, there's two parts. Basically, what you have, this is the list, remember, crate decals. This is all the definitions of all the crates. And then this is the specific crate that we're compiling right now. It's kind of the local crate. This will always be a member of this. We should probably actually add that. I'm going to do that for fun. So let me show you what I'm doing here. I'm adding a precondition to this function. Yeah, there we go. So this weird notation means, well, Racket people like their leading. I shouldn't be so judgmental. This Racket notation of a hash sign means funky stuff, and in this case, it's a precondition. So this is a regex thing that must evaluate to true. In question mark is actually a function I defined that I don't think is imported here. I think it's in logic and bracket, if I'm not mistaken. It's going to be dot dot, 2 levels of dot dot, right? Or no, one. So we should be able to go to definition now. It's a very simple function. In is true if this first term, if there is some term in this list, so it takes one. A term is anything, right? Term could be any. It's a grammar for anything. One thing in a list of things. If that first thing, if there is something in the list that is alpha equivalent, meaning can have variables that are bound, can be renamed to term 0, then it's true. Otherwise, it's false. So it's sort of what it sounds like it is. So yeah, with this precondition now, if you tried to call this function with some crate that wasn't in the list of crates, you would get an error. Okay, so anyway, that little aside, we are now going through, this is the current crate that we're compiling. This is the list of all the items in the crate. This dot 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 means match more than one thing. And so what we're going to do is we're going to map over these items and produce 2 sets of goals. The first one is the kind of standard goals that tell you that a given item is okay. So these would be for any, like for any struct or any trait, these are the base conditions that have to be met. And then we have this function laying item okay goals that says, are there some extra rules built into the language that are specific to this particular trait, and not shared by all traits, or specific to this particular struct or whatever. Laying item is a term from Rust C that you may be familiar with.
That's something that we created yesterday for drop.
Yeah, we made it for drop, but we're going to use it again. And the thing about the laying item okay goals, if you go to that definition, is that for a given crate item, it returns a list of goals, which may be the empty list. And the reason we do that is for things that are not laying items, we just return the empty list. For things that are laying items, we could return multiple goals or whatever we wanted. The reason that's relevant is here we're mapping this function over, we're saying do that for every crate item. So we're going to get a list of lists, right? This first dot 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 means for each crate item. And then inside of that, there'll be a list of goals. That's what the second dot 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 is telling us. And so then we can use 2 dot dot dots here to flat map. This is basically concatenating 2 lists. Take all the regular goals and the flat map of the language item goals and put them all into one big old list. Learn to love this dot 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 notation. It is awesome, but also used everywhere. Does that make sense? questions on that? Okay. So, right. So here we have this laying item OK goals function. This is the rule for drop. We're going to do a similar rule for copy. So I'm going to copy this. No, I won't copy it because it'll be clearer if I start it over, I think. You can see this is like the main place I use brackets. I don't know why. It's just a convention I stole from them, I guess. Inside a meta function, I usually use brackets for each possible case. So the first thing in each case is, each case has this form. It begins with, let's steal this one. It begins with, oops, sort of, why did that not work? Sometimes there's like a race condition in this. I've noticed this before in the VS Code extension, that when you hit command copy, it takes a little while to actually do the copy. I don't know why. And so I'm too fast for it or something, and I end up pasting random stuff. I think it has to do maybe with running over SSH. So, right, so this is the name of the function, and then these are patterns to match against each parameter. So in this case, we're getting in a crate item. And so we're going to match only those crate items that are in impl, and we're going to extract out, here's the generic types. This is the name of the trait being implemented. We're going to use copy. This is the list of parameters. Copy only has one, so we just need one, and we know it's a type. Ordinarily, you might have like a lifetime or whatever. This was a generic trait. If this was partially Q, there would be two types in here. And then this is the list of where clauses on the impl. This is the list of items in the impl. Copy doesn't have any, so we could just put an empty list there. So let's write our comment. What we're going to do if you implement the copy trait, when you implement the copy trait, some struct foo of t, all the fields in that struct, enum, union, etc., must also be copy. So here is an example that does not meet this condition. Well, actually, no, let's do that. So for this example, right? So let's say we have this struct, and it has like a field, I don't know, vec of t or something. What we would generate is a goal that says, for all t, meaning all the type parameters of the struct, assuming that the where clauses hold. So assuming t debug. Oh wait, actually this is the wrong rule. This is the drop rule, but what we actually want is something slightly different here. We want to say, for all u, meaning all the type parameters on the impl, assuming that the conditions on the impl hold. Let's take out this debug equality stuff. That's not very exciting. Assuming the where clauses on the impl hold, then there exists a set of type parameters, t, which is this comes from the struct. Basically, we're going to match against the struct here. So we're going to say that there's given some type parameters t for the struct, where this type equals that type. So foo of t is foo of u. Then, and now we're going to add in, for each field in the struct, vec of t had better be copy. That's the condition we want to be met. I don't know how many parentheses I need. Maybe one more. Okay. Does that sound right? Does that look reasonable? Also, give me a second. I'm getting a call I have to take. Okay. So yeah, so that's the goal. That's basically the rule in the general form. And in this case, it won't be provable. Because vec of t copy is not true for any t.
What if that foo u equals foo t is unsatisfiable? Or like, you know, if the expression ends up being weird in some way so that you can't, like, wouldn't this end up being trivially true or something?
More the opposite. If this for some reason is not provable, then, well, there's something I sort of left implicit, but this is, how do you do that? All of these things have to be true, right? So we wouldn't be able to prove this goal if for some reason this were not equal.
I see.
Okay, so now we want to generate this. We have 10 minutes. I think we can do it. But let me skip this. We're going to need some of this stuff. Oh, I didn't finish telling you the structure of this stuff. So this is the thing. This is the pattern we're going to match against. And then this is the return value. Usually I just put an XXX there or something because there's this weird evaluation order where, you know, it starts by matching the pattern, then it executes all the wheres and where errors I'll get to in a second, and then it generates the return value. So I like to put something there so I don't forget, and then go write the code. So what is this where and where error? So where is
I have
basically.
a question.
Oh yeah,
Real
go.
quick. The implemented constraint on u, does that in this example, not in drop, does that come from the, that comes from the impl, not from the struct definition? Because in the drop.
Correct. There's a difference between the drop rule and this rule, that the
Yes.
drop is trying to say, is saying something is true for every instance of the struct. But in this rule, we don't need it to be true for every instance of foo. We only need it to be true for those types of foo that are copied. So we're actually quantifying over the impl and not the.
And that's part of why the parameters are swapped. So that should be evident.
Yeah, exactly. That's why I'm
gonna do that.
Oh, thank you. Yeah, I'll make it a little clearer.
Any objections? Okay.
There's one thing that you're not asking, but maybe you should be, is what if we're going to see that I'm just going to copy and paste these rules in much like this way. And you might be wondering, what if T and U, you know, here I gave them different names, but what if they were the same name? Wouldn't it be shadowed? Or would there be a problem? The answer is yes, there would be a problem, except that redx, we've told redx about the binding and it's going to do the renaming it behind our backs so that there's never any shadowing. So we don't have to worry about that, which is kind of cool. So, right. So what are we doing? So I matched against the impl. What I'm doing here is just destructuring some of these non-terminals into their pieces. Like here I said, we have some type. Well, what I want to say is if that type is an ADT, right? So I'm putting the where means if this is not true, then move to the next case. Right? So if this destructuring, if this pattern match fails, we're going to go and execute this next case. Other times, actually most of the time, I end up writing where I find, at least I write where error means if the pattern matching fails, some assumption of mine is wrong, there, you know, throw an exception, something's broken. So basically this is an irrefutable match, or sort of expected to be irrefutable. It's a pretty important distinction for debugging, so it's worth making it consistently. Otherwise really weird stuff happens where it just goes running off into matches you don't expect. So right, so we're going to say, the thing is this, there could be many kinds of copy impls that are not of ADTs, and those might be okay. You may have some more rules down there, but for now we're only concerned about ADTs, so we're doing a where, a fallible where. And then this function, what this does is it goes off and fetches the definition, given the full set of items, all the crates, fetches the definition for this name. So I assume everything has distinct names, make my life easier, right? And then this pattern is matched against the definition. Actually, what I should be writing here, hold on a second, grammar. what is this thing? Decal grammar. So the definition is this ADT contents. And actually, I think it would be good to not write underscore, but write ADT. So there's a subtle point here, which is that although I wrote ADT ID, indicating this is the name of an ADT, actually from redx's perspective, well, it's not in this list, but there's another list somewhere else that's similar. All IDs are some kind of variable name. Like it doesn't really know, that just means string in short. It means a string that doesn't show up anywhere else in the grammar. So maybe this isn't really the name of an ADT, maybe it's the name of a trait or something. So that's why I make this next thing fallible too, because once I've found the definition for ADT ID and it indeed matches the form of an ADT, I know it really is an ADT. But I find it pretty useful to distinguish, what I think it is, but that's an important thing to keep in mind. I've occasionally written code that was bogus for that reason. So, right, so now we have an ADT. This is the definition of the struct. In other words, here's the generics. Here's the where clauses. We don't actually care about the where clauses from what I can tell. So I'm going to get rid of them. And now we have to generate, I don't think we need to do anything else. Let's find out. So we're going to generate this return value. One thing is we're supposed to generate a list of goals. So if we need another parentheses, okay. We're going to do for all. That's this for all here. And then we wanted for all u. So that's for all the variables on the impl. Now we're doing an implication. If the where clauses on the impl are satisfied, then actually I could do this. Oh no, yeah. Okay, before I go further, there's a subtle point here. Where clauses, I use that to refer to the Rust syntax. And actually, yeah, I use that to refer to the Rust syntax. But what we're doing now is generating a logical predicate, and those are richer. There are more kinds of predicates, and they don't map one-to-one to where clauses. Like where clauses can be mapped to predicates, but not vice versa. And so what we actually want is not, we don't want to put where clause here. We want to use this helper function that converts a where clause to a hypothesis, because what we need here is a list of hypotheses. And so what I'm doing here, when I write it like this, I'm actually mapping that function across this whole list.
And in fact, I believe if you look at the drop implementation, we had to use a where clause as a goal.
Yeah, we're going to get to that. Oh, well, no, we won't, I guess. But yeah, in the case of drop, we used some of the where clauses were things that we got to assume. Those we convert with the hypotheses function, and others were things we wanted to prove. So in that case, we use the goal function. I actually think, because I think that right now there's really no difference between these functions, but I keep the distinction for, like, in other words, the syntax of goals and hypotheses overlap. So they will actually return the same thing, but it's useful to make the distinction just for readability.
Does the syntax of where clauses and hypotheses overlap?
It does, which I think we should change. I guess right now it partially overlaps, not always. In particular, outlibs relations are different. I think we should change it so that where clauses look more like Rust. Like I would like you to not have to write implemented in the Rust-like syntax, and get translated. And there would be two advantages. One, the syntax would look more like Rust, and two, you would fail faster when you forget to call this function, because things would not pattern match. So, right. I'm just going to go quickly because we're running out of time, but what we need is, we need to do, there exists for all the variables in the ADT, we need to prove all the following things. We need to prove that the type in the impl, which is tie-impl, is equal to the type from the ADT. So this is going to be a rigid type named after the ADT with oh man, we need this code. Hold on, forgot about this. Okay, so what's happening here? This is a list of pairs. We don't need the kinds, we only want the names of the variables. So we're going to just pattern match against the list of pairs and pull out the second half. This is the type, like foo of t. We can put it in there. And then we also want to say, oh, we're not quite there. I'm gonna have to go because I have this other meeting. But what we should add, I could push this somewhere if someone wants to take a stab at it. But what we should add now is we need to, here's the ADT variance. We need to extract all the fields, like tie of field. Need to add a goal, like implemented Rust copy tie of field, something like this for each field of each variant. Right. So it's gonna look like that when we're done. Did I get enough parentheses? No, there. Oh no, I did. I had them down here. Okay. But all right, I'm gonna stop. We can discuss on Zulip after. And thank you all for attending.
Awesome. Thanks, Nico.